All right. It is my pleasure to announce the speaker today. We're going to hear from Sahil Singla, who's a PhD student at the University of Maryland, College Park, has his undergraduate degree from IIT Delhi in computer science. His research interests are in adversarial robustness and the interpretability of deep neural networks. And his recent work is focused on provable defenses against adversarial attacks and interpretability using robust models. And with that, take it away.
Hello, everyone. Myself, Sahil. I'm a third-year PhD student at the University of Maryland. It is a great pleasure for me to talk to everyone here at Stanford. So I would like to sincerely thank the organizers for the invitation. Today, I am going to talk about my paper titled Understanding Failures of Deep Networks via Robust Feature Extraction. This work was carried out during my internship at Microsoft Research with my amazing collaborators, Nushi, Shah, AJ Kamar, and Eric Horvitz. In the last 10 years, we have seen multiple advances in machine learning, and we have seen ML systems being deployed in the real world. But together with their deployment and successes, we have seen multiple cases of failures that are unpleasant for the end user, and the net outcomes do not necessarily improve human productivity. So, an important question is, can we somehow identify the underlying factors responsible for such failures? In this work, we make some progress in that direction. So, what does error analysis even mean in the context of machine learning? Well, the honest answer is that there is no standard definition for it, but in the context of what may be important for practitioners, let us try to define it. We can analyze errors at the instance level. The goal here is to understand why a model failed on a single image. Consider this image. The true label is insect, but the model predicts dog. Can we somehow make the image look more dog-like, or similarly, more insect-like, to identify the underlying reasons for failure? Similarly, we can analyze errors at the group level. Here, the goal is to identify the patterns of failure in a group of images. For example, given a set of images on which the model incorrectly predicts the class syringe, here are some correctly classified images and some incorrectly classified images. Using the techniques we will soon discuss, we discover that one of the underlying patterns of failure is the missing syringe markings. Error analysis at the group level is the primary focus of this work. Now, why do we even need error analysis? The problem is most of the bias and performance discrepancy issues in machine learning start with data problems, but they get finally baked into deployment through poor performance reports. For example, most of you would have seen some article in the media claiming that a model is 90% accurate using a single score to describe the model performance on the whole benchmark. Unfortunately, we also do this in our tables in research papers, and there are Kaggle competitions where the leaderboards rely on a single aggregate measure of performance. The problem here is that a single aggregate metric assumes that the model performance is uniform across the whole benchmark. In the real world, we know that model performance can be wildly non-uniform. Thus, identifying clusters of data with high rates of failure can improve model performance in the real world. For example, in the gender shades study conducted by Joy et al., the authors discovered that the error rates for gender detection are much higher for women with a darker skin tone. Now, there is a tool by Microsoft called Error Analysis for identifying such clusters of failures. We augmented the gender shades benchmark with features from the Face Azure API and analyzed the gender detection model studied in the gender shades paper using this tool. On the left-hand side, we see the different features extracted from Azure API like gender, face hair, skin type, etc. On the right, we show a decision tree trained to distinguish between when the model is right and when it is wrong. Darker red means higher error. And if we follow the red critical path here, we can see that the overall error for the whole benchmark is initially about 5.5%, but it becomes higher and higher if you are a woman, if you have no makeup on, you have short hair, and you are not smiling. Now, for the face dataset, we can collect such metadata cheaply from various sources. But for more general datasets, we run into some practical problems with this approach. Consider some sensitive applications such as skin cancer classification or chest X-ray pneumonia detection. For such problems, the metadata might not always exist or it can be expensive to collect. Moreover, even if we were to do a very extensive collection of metadata, it may not cover all the features that a machine is paying attention to simply because the human and machine perspective can be very different. Thus, we need a way of explaining failure from the machine point of view. Now, to analyze errors from the machine perspective, we ask ourselves the question, is it possible to use the internal representation of a neural network itself as the metadata? Previous work provides some evidence that this internal representation can capture important visual attributes. So, what do we exactly mean by the internal representation? It can be defined in different ways, but here is what it means in the context of this work. Given an image, for most modern neural network architectures, you pass it through a set of convolution and activation layers to get the feature map. Next, you apply a global average pooling layer to get a vector representation for the image. We call this vector, that is the output of the global average pooling layer, the internal or feature representation of a neural network. Now, let us see how we can use this internal representation for error analysis. Here is the workflow. For a trained model, our goal is to discover the underlying patterns of failure using a given set of images and their labels. In the first step, we extract features from the images such that each feature encodes some interpretable visual attribute. This gives us a vector representation of the image. Now, once we have this representation, our next step is feature identification. Here, our goal is to identify the set of features that are highly predictive of failure. This gives us a desired set of features. Once we have identified this set of features, the next step is feature visualization. Here, we want to be able to visualize the features so that a user can understand what they mean and how the presence or absence of a certain attribute in the image increases or decreases the error rate. This allows us to discover the failure modes in the model. We call our method bar loop. We will now discuss each of the components of our workflow. Let us for now assume that we have already extracted the features from some standard pre-trained neural network. First, let us try to visualize these internal features to understand what they mean. Now, how do we visualize these internal features of a network? One straightforward approach can be to find images in the training data that give the highest activation values for the feature. Let us look at an example using this technique. Here, we select a feature that is known to be highly predictive of the class promontory. Since the word is slightly unusual, we have included its definition. Promontory is a raised mass of land that projects into a body of water. Here are the images that maximally activate the feature. Now, the problem is, from the visualization, it is not clear if the model is focused on sky, water, or ground. Can we do better? One possible solution can be to generate a heat map to visualize what the model is looking at. But how do we generate such a heat map? Given an image and the feature index of the feature we are interested in, we first pass the image through a neural network to get the features. Now, We are interested in the feature at the ith index. We will use the index of this feature in the previous layer to get the feature map. Next, we simply normalize the feature map to lie between 0 and 1 and resize the map to match the input size. This gives us the desired heat map. Let us look at some visualizations using our heat map on the original example. Again, these are the most highly activating images. Here are the heat map visualizations. Darker red means the region is more important for the feature. We observe that in the last three images, the model focuses on ground. However, in the first three images, it is focused on water and sky. Clearly, this does not seem to solve our problem. So, is there another way to visualize the feature? Can we somehow change the image itself to make the feature more visible? Let us discuss one possible way we can do that. Again, given an image and the feature index of the feature we are interested in, we pass the image through a neural network to get the desired set of features. Again, we are interested in visualizing the feature at the ith index. We can simply optimize the image to increase the value of the desired feature to get the feature visualization. Here, the L2 constant of rho can be chosen to control the amount of change allowed in the image. Rho is usually chosen to be large so that the new image looks substantially different from the original to a human. This is what we call the feature attack. But does a feature attack even work? To answer this question, let us do a feature attack using the feature we considered previously. Again, these are the most highly activating images. Next, we do a feature attack using the same standard pre-trained neural network as before. We observe that the new images look identical or at times noisy compared to the original. Clearly, it doesn't work. Now, there are various tricks to visualize these internal features using optimization. Some of them are described in this excellent blog post by Chris Ola. However, it is unclear if the visualization after applying these tricks remains faithful to the underlying model. So, how do we fix this problem? We use the prior observation by Madhuri et al. That the features of a robust model can be visualized directly using optimization. For those who don't know what a robust model is, we will be discussing it in the next slides. Here, we again select a feature highly predictive of the class promontory from a robust model, and these are the most activating images. Doing a feature attack gives these new images. From these new images, we observe that optimizing this feature makes the salient feature of ground in the original image more prominent. It is now clear from this visualization that the model is focused on the ground. To understand what a robust model is, let us first discuss a very intriguing phenomena in machine learning. Given an image correctly classified by a neural network as a pig with high confidence, we can add a very small amount of noise so that each pixel that lies between 0 and 1 is changed by at most 0.005, so that the resulting image looks identical to the original image to a human, but the model now classifies it as an airliner with high confidence. Such a perturbation is called an adversarial perturbation. The resulting image is called an adversarial example. It has been empirically observed that for almost all inputs to a neural network, we can find such adversarial example. Since the two images look identical to humans, our goal is to make neural networks robust against such adversarial perturbations. Now, how do we train such a robust model? Given pairs of training images and labels X, Y, the prior we want to impose on the model is that a small change in the image should lead to a small change in the feature representation. The way we do it is, we first find an input that maximizes the cross entropy loss in an L2 ball of some given radius rho. Here, rho is chosen to be small so that x star looks identical to x to a human. This is the equation for maximizing the cross entropy loss for an input in an L2 ball of radius rho. Here, X star is the adversarial example, P are the softmax probabilities, and L is the cross entropy loss. Next, we want to minimize the network parameters so that this worst case cross entropy loss is minimized. The model that we get after this training is called a robust model. We also observe significant differences between the heat maps for a standard and a robust model. Recall that in the heat map for the standard model, it was not clear whether the model was focused on ground, sky, or water. However, in the heat map for the robust model, we observe that the model is always focused on the ground. Now, let us look at our complete feature visualization methodology for the same feature using a robust model. This is the visualization we will be showing to the users of Barlow to help them understand the semantic meaning of a feature. First, we show the most highly activating images from the training dataset along with the true labels. Next, we show the heat map visualization. Next, we show feature attack images generated by optimizing the original images to increase the feature value even further. This confirms our intuition from the heat map that the feature is focused on the ground, not water or sky. Now, coming back to the workflow, for feature extraction, we initially used a standard neural network, but it did not give good visualization. So we decided to use a robust neural network for feature extraction. For feature visualization, we use the most highly activating images, heat maps, and the feature attack. Let us look at the last and final piece of the workflow, that is, how can we identify the set of features that are highly predictive of failure? In order to identify the most important set of features, let us first introduce some definitions. Given a set of images S containing both correctly and incorrectly classified instances and their failure labels, consider a subset of images C. We define the error rate of C as the fraction of images in C that are failures. Similarly, we define the error coverage of C as the fraction of failures in the complete set S that are covered by C. The base error rate is the error rate of the complete set S. Now, let us try to understand our exact objective for error analysis. Our objective is to identify clusters with error coverage above a certain threshold and error rate significantly higher than the base error rate. In this illustration, here is an example of a cluster with high error rate but low error coverage. As you can see, the number of red dots that are failures in the yellow circle is very small. This is a cluster with very high error coverage but low error rate. We want a cluster that looks like the rightmost one so that it can explain a significant fraction of errors with high accuracy. Now, how do we find such clusters? Given a trained neural network whose failures we want to explain, it can be a non-robust model. In our experiments, we observe that error analysis for the whole dataset does not give good results. Thus, we first create a group of images such that for all images in the group, the model prediction or the true label is the same. Next, we extract the feature representation from a robustly trained neural network. This representation can be of a large size. It was 2048 in our experiments. Since decision trees are known to suffer from the curse of dimensionality, we select the most important features for predicting failures using some standard heuristic. This reduces the dimension of feature representation to 20. Next, we train a decision tree to predict failure. From the trained decision tree, we identify leaves with error rate higher than base error rate plus 0.1 and error coverage above 0.2. Here are some examples of failure modes discovered by Barlow using a decision tree of depth 1. We emphasize that all these results are using a non-robust model. This example uses grouping by the predicted class. The predicted class here is Rhodesian Ridgeback. The base error rate is 20.93%. Our decision tree discovers that if feature 1634 is less than 0.344, new error rate is 31.84%, about 11% higher than base error. Now, what is this feature looking for? These are the most activated images. The heat map visualization suggests that the model is looking at the collar of a dog. Next, by doing a feature attack, we observe that new images are full of dog collars. This allows us to diagnose that presence of collar is an important feature for correctly predicting Rhodesian Ridgeback because these dogs are likely to co-occur with their collars. The important point here to note is that this is just a spurious correlation. Here is another example, again using grouping by prediction. The predicted class here is syringe. The base error rate is 20.2%. Our decision tree discovers that if feature 638 is less than 0.042, new error rate is 35.2%, about 15% higher. Now, what is this feature looking for? These are the most activated images. The heat map visualization suggests that the model is looking at the syringe measurements. Next, by doing a feature attack, we observe that the new images are full of measurements. This allows us to diagnose that presence of measurements is an important feature for correctly predicting syringe, again because these syringes are likely to co-occur with measurements. While this is not exactly a spurious correlation, this is an example of an overemphasized feature. That is, the model is giving excessive importance to the measurements of a string and not to other features. Here is another example where we group images by class labels. The class label here is monastery. The base error rate is 31.84%. Our decision tree discovers that if feature 995 is less than 0.143, new error rate is 63.45%, about 31% higher than the base error. Now, what is this feature looking for? These are the most activated images. The heat map visualization suggests that the model is looking at the greenery. Next, by doing a feature attack, we observe that greenery is amplified in the new images. This allows us to diagnose that greenery is an important feature for correctly predicting monastery because monastery is likely to co-occur with greenery. This again is an example of a spurious correlation. Here is another example using label grouping. The label class here is purse. The base error rate is 30.85%. Our decision tree discovers that if feature 1456 is less than 0.364, new error rate is 41.79%, about 11% higher. Now, what is this feature looking for? These are the most activated images. The heat map visualization suggests that the model is looking at the buckle of a purse. By doing a feature attack, we observe that images are full of purse buckles. This allows us to diagnose that presence of buckle is an important feature for correctly predicting purse. We emphasize that more than 40 such examples are given in our paper. Now, returning to the error analysis workflow, we know how to extract, identify, and visualize features. The next step is to evaluate the failure modes. Now, can we somehow evaluate the decision tree automatically? The usual metrics for evaluating decision trees are precision and recall. Consider the decision tree on right-hand side. Since the error rate is below 0.5 in both leaf nodes, precision and recall are both 0. However, since the error rate of left node is significantly higher than the base error rate, the left node is highly predictive of failure. Ideally, we want a metric that conveys that the tree contains some leaves with error rate significantly higher than the base error rate and moderately high coverage. To capture this idea, we introduce a new metric. First, recall the definitions of error rate and error coverage. For each leaf, the error rate or ER equals the fraction of instances in leaf L that are errors. The error coverage or EC equals the fraction of errors in leaf L out of the total number of errors in the dataset. By definition, the sum of error coverage across all leaves equals 1. To evaluate a decision tree, we compute the average leaf error rate weighed by the error coverage values across all leaf nodes. The resulting metric is called average leaf error rate or ALER. The key property that makes this metric useful is that if it is greater than Q, this implies that there exists a leaf with error rate greater than Q. Thus, the difference between average leaf error rate and base error rate can be considered as a heuristic for the performance of decision tree on error analysis. Let us look at an example. Consider the tree in the previous slide. For the left leaf node or leaf 0, we have error rate equals 0.454, error coverage equals 0.5. For the right leaf node or leaf 1, we have error rate equals 0.128, error coverage equals 0.5. Average leaf error rate can be computed using the given formula. It is equal to 0.291. And we know that leaf 0 has error rate greater than 0.291. We now report our results for the factors that influence the effectiveness of error analysis. In this slide, we compare between the two possible grouping strategies, namely label and prediction grouping. When inspecting the errors of a standard model, we observe that grouping by label gives better results using our proposed metric. Similar results can be observed when inspecting the errors of a robust model. As you can see in both these plots, the metric has higher value for label grouping. Here, we compare between the effectiveness of error analysis when inspecting the standard and robust models. When inspecting the errors using label grouping, we observe that robust model gives better results. Similarly, when inspecting using prediction grouping, we again observe that robust model gives better results. This suggests that it is easier to find errors for a robust model. In this slide, we compare between the results using decision trees of depth 1 and 3. When inspecting the errors using label grouping, we observe decision trees of higher depth give better results. Similar results can be observed when we use prediction grouping. For all 1,000 classes in ImageNet, we trained decision trees using both standard and robust models, depths 1 and 3 of the decision tree, and both label and prediction groupings. In the last column, we showed the fraction of classes for which we could find at least one leaf satisfying our condition, that is error rate greater than base error rate plus 0.1 and error coverage above 0.2. In all different cases, we are able to find significant number of classes satisfying our conditions for the existence of failure modes. Importantly, only for the case of a standard model and decision tree depth 1 and prediction grouping, we find the minimum number of such leaf nodes, which is 211 out of 1,000 classes. We also did a crowdsourcing study using Amazon Mechanical Turk to evaluate the effectiveness of our feature visualization methodology. Turkers were shown 3 sections, each containing a component of our visualization. Section A for the most highly activating images and labels. Section B for the heat maps, and Section C for the feature attack. They were first asked to describe the visual attribute in one word and one phrase. Next, how easy it was for them to describe the visual attribute and how confidently they were able to understand the feature. Next, which section was most useful for understanding the visual attribute? Section B, Section C, both or none. Here are the results for questions about confidence and ease of describing the said feature. We observed that workers were able to describe large number of features, that is more than 800 out of 1,200 features with high Likert score for both confidence and ease of description. Here are the results for the last question, that is, which section is most important for understanding the features? We observed that workers found heat maps to be the most important. Feature attack images were also valuable both individually and with heat maps. Only 0.92% of all features received none as the majority vote from all workers, suggesting that our visualization is effective for a large number of features. To evaluate the usefulness of Barlow for error analysis, we also conducted a user study with 14 machine learning practitioners at Microsoft. Participants were shown two failure modes discovered by Barlow and asked the following question. For the second question about whether the feature is a spurious correlation, we found that participants were able to identify several surprising spurious correlations. For example, P12 identified that the model uses human hair for detecting seat belts. P5 identified that model uses green background for detecting tiger cats. P7 identified that model uses face of a dog and not other features such as legs, hair length, and hair color. For the third question about action items for mitigating failures, results are as shown in the plot. Data collection was the most important action item according to the participants. These results suggest that Barlow can be used for iterative refinement of trained models to mitigate failures. In conclusion, we introduce a method to analyze the failures of machine learning models without manually annotating for visual attributes. We conduct user studies to evaluate the interpretability of features and usefulness of Barlow in real-world settings. Our next steps are to analyze failures in radiology datasets using Barlow. Code is available on GitHub. Here are some preliminary results on the Chexpert dataset. For the predicted class plural effusion, here is a visualization of a feature highly predictive of this class. These are the most activated images. Here is the heat map visualizations and the feature attack visualization. We emphasize that it is also possible to visualize the same feature by gradually increasing the intensity of the feature attack. In the top row, we show the original images. As we go from top to bottom, the intensity of feature attack increases so that the images most intensified by the feature attack are in the bottommost row. Please let me know if you have any questions regarding our work.